world is becoming a louder place. As populations grow, silence and quiet will become increasingly rare. Silence and quiet are especially important for us students because it is often the time and place that is silent where we can focus, critically think, and reflect our best. Reflecting is especially important because that is how students process their information for themselves and learn to apply it. If nothing is done to preserve the silence, cities like Linwood and Edmonds, where we are now, will become as loud as Seattle. Seattle will become as loud as New York, and New York will become as loud as New Delhi. This is where noise mitigation comes in. Noise mitigation is the act of reducing the effects and impacts of noise pollution. Noise pollution is the loud noises on the highway, the garage band playing way too loud, and every tardy alarm ever. So our overarching goal was to find the materials and its properties that make it the best at mitigating sound. Our hypothesis before we started doing any research was that the materials with the most air pockets in them had the highest ability to mitigate sound. Our logic was that the air particles would trap the sound energy and convert it into other forms of energy. Okay, before we go on, we need to understand the physics of sound. Sound is a mechanical wave. That means it requires a medium for it to travel. This is opposed to an electromagnetic wave, which can travel through vacuums. So, by deduction, if there is a vacuum, there will be no sound in that vacuum. Also, there is a common misconception that sound is shaped like a sine wave. However, this is actually a graph that shows how sound travels. It fluctuates in pressure as the density of the molecular interactions change. Sound has to travel by at a molecular level where each molecule interacts with another by passing on sound energy. In areas with high density and pressure, the sound energy is greater and they are called compressions. With low density and pressure, these instances are called rarefactions. Another thing to note is that sound travels in all directions, and when it travels with distance, it does not lose energy, it simply becomes spread out more. Also, it is important to understand that the conservation of energy of sound. Sound energy does not disappear. It gets transferred. So sound energy comes from a vibration. The vibration causes the other particles to vibrate as well. And the vibrations in the other particles are transferred as work, so they move. And the movement eventually stops when the friction, which turns the work energy into heat energy, stops the movements, and there is the process of how sound energy becomes heat. Also, sound travels very differently depending on its state of matter. Sound travels the worst in gases and the best in in solids. Liquids is somewhere in between. As you can see, in gases, there is a wide distance between the molecules, which causes them to expend more energy. And this can really be shown if you imagine two people throwing a ball. The person over here will get very tired if the more balls they throw. In a solid, you can simply pass on the ball to each other. And this becomes more efficient and more effective for sound to travel, as you can see how it builds up and stuff. I'll now hand it off to Zach, who will explain our process in doing the experiments and analyze the data.